Hello everyone, and my name is Ziyi. I'm from Northwestern University and currently a PhD student. I'm from Computer Science Department. And today I want to talk about our work, which named Take a Step Further Understanding Page Spread in Linux Kernel Exploitation. And this is also a joint work between Northwestern University and Arizona University and ASU, Arizona State University. And first, let's talk about the vulnerability in Linux kernel. As we all know, Linux kernel, as one of the most important infrastructure in the digital world, suffer from different types of vulnerability, such as out-of-bound. And it happens when attackers access a memory address based on certain object, but the address is actually out of the current object's boundary. And use after free, known as UEF, it relates to access the object after it has been freed. Double free, which is a special type of UEF, it indicates to free an object twice and confuse the system. And invalid free is freeing a fake object or an address, which is not the correct address of an allocated object. And behind these different kinds of vulnerability, the exploitation highly rely on the mechanism of Linux kernel memory management. Basically, Linux kernel memory management can be divided to two different kinds of allocators, heap allocator and page allocator. And as for heap allocator, also known as slab allocator, it uses for kernel heap object-based allocation, and the cache there can be grouped to different small groups, and it relates to the different size, and also there are some we call dedicated caches there. When a new slab is created, usually it will relates to the new slab pages allocation, and the slab is built based on those different new slab pages. And for page allocator, it is fundamental mechanism for system memory management. Many other operations directly or indirectly relate to page allocator, such as heap allocation. So the state-of-the-art exploitation technique currently indicates to DirtyPage, which is a heap-level exploitation technique. It published in CCS and Black Hat USA 2 years ago. And first, it uses an object temporal vulnerability as a starting point. In the next step, it maintains a reference to the writable object spot, then frees a writable object, and reclaim the free slot with privileged objects. Now you have a reference to privileged objects. And by doing so, actually, you can have the permission to modify the critical fields, like password field, which actually relates to the real-world user permission. So another one is Wait a minute. Yeah, so another one is cross-catch. So cross-catch is like, it is used for attack dedicated catch. Imagine you have a reference to a normal catch. You maintain a reference and free object A and reclaim with object B. Now you can transfer your reference to another catch, which is usually the dedicated catch. And this is kind of like a critical type confusion in Linux kernel exploitation. So as we can see, all this previous situation relates to free pages reclaim. So on the one hand, when slab is empty, sometimes system will discard the current empty slab, and it will trigger the free operation of the slab, and eventually all pages in the slab will be freed. And on the other hand, when a new slab is going to be created, kernel will just invoke some allocation function, and inside this function, the pages will be allocated for the new slab caches. So I think as we can see, the allocation and the free for pages are actually the fundamental operations for the slab allocator or heap allocator. So there is a question here. Is that possible that we do not reclaim pages by the heap allocator or slab allocator, which means we skip the slab allocator and we reclaim the page by direct page allocation? So let's first have a flashing back. So dating back to like 9 years ago, there's a paper talking about some similar things, but due to the memory increase and the restriction about the memory, currently for the user space process, this kind of attack is hardly to use today. So let's come to the root cause of the page spray. Dive into kernel code base, you may find some interesting stuff. Like there are some interesting design. First one, we call it like copyright pattern. There are two subtypes of that. Like first one is rare page level buffer, which is directly use page buffer for the massive data. Another one is nonlinear page flags buffer, which is used in code logics about the SKB operations in networking subsystem. When there is too much data as networking message, and kernel will use page flags buffer to store that kind of data. And another one is like another one we want to talk is like mmap and the zero call basing. The second design here is related to the mmap. In some kernel logics, you can directly allocate pages and then remap a direct allocated page to a user space process and access this page from user space, like putting your own data into the page or read some data from the page. And by using mmap to trigger that kind of logic, you will get a user space virtual address for the target kernel page, which makes attackers easy to access them. So for the module of page spray, here is an example of it. If you have a double free vulnerability, you trigger double free in vulnerable object and free all the object except the victim object. And after that, kernel at this moment could discard the whole slab because it thinks the slab is empty. But actually, the victim object is still on the slab, but the page has been freed. Then you can trigger the direct page allocation and put your own data onto the page. Finally, your data will have kind of like an overlap or overwrite the victim object. So there are multiple callsites in kernel which is related to that kind of logic. We propose some static and dynamic methods to analyze them and to conduct the analysis. Here are some results, and all of those kind of call sites we found can be reached and triggered through the system call from user space. And when it comes to the exploitability, as for evaluation, we evaluate the page spray based on multiple aspects. The first one is exploitability. We perform page spray to different real-world CVE. Actually, it's 15. And some of them is mobile device related. Some of them include the cross-cache operations. Also, we talk about one special CVE case in our case study part. So for the stability, also we evaluate the stability of page spray exploitation under two different system workloads, idle and busy. Because we know in real-world environment, the system workload will not always as what we expect. So here is a GitHub repo link of our stability and exploitability results, and you can access the exploits we write here. So as for the mitigation, discussion, yeah, actually, when it comes to the mitigation, the lessons we learn here is like page spray is kind of page level memory reuse. And the page level memory reuse is pretty much very dangerous. And mitigate it by a straightforward method could be like we just use a different memory area to isolate the page allocation, which relates to the page spray call sites. Like we can just simply use the different get free pages flag or something like that. And at that kind of situation, even the page spray can be triggered. Overlap between critical objects and data won't happen. And there is another external mitigation called slab virtual. I'm not sure if any one of you heard of that. This kind of mitigation is more fancy. It's like trying to prevent slab virtual address reuse. And it is designed and proposed by Google. So finally, we got to the real-world part. In the real-world part, our team write some real-world exploits and about the page spray. And there are two CVE, one CVE we exploit in Google Pixel and Samsung. All of them are mobile device. And there is another talk in Black Hat USA last year named Bad IOU Ring, and also talk about the page spray. And we also use the real-world CVE in Google KCTF and Typhoon Pong. And the case study part, we talk about like how page spray can be used to facilitate some intractable exploit. So when it goes to the conclusion part, page spray provides comparable, even superior exploitability and stability in real-world scenarios. And the root cause of page spray is associated with some machinism in Linux kernel's design. And we should rethink the reuse of pages, design and introduce more powerful mitigation into kernel to mitigate the page spray attack. And thank you.